Hi. Our topic for today is section 6.5, which is partial order relations, and that's probably fairly simple and quick section. And with this section we finish chapter 6. So 6.5, partial order relations. So here are a couple of definitions. Definition, a binary relation R on a set A is antisymmetric if for every xy in A, xry and yrx implies x equals y. This is a nice elegant definition of this property, but probably it is better, maybe even more intuitive, if we play a little logic on it. So comment. If we do contraposition of this, instead of P implies Q, we do not Q implies not P, then we get the following. If x is not equal to y, the negation of this conjunction, according to De Morgan, is disjunction of negations, not x or y, or not y or x. But then even better, if you call this P and this Q, then we use again that not P or Q is equivalent with P implies Q. So we get the following: if x is not equal to y, then x r y, because that's P. Not P is everything, so P is just what I included in a curly bracket, implies not y r x. So if you read it this way, it says the following: outside of diagonal, wherever two elements are related in one order, it's prohibited that they are related in the opposite order. So for example, let me make a table like 4 by 4. 1, 2, 3, 4, 1, 2, 3, 4. On diagonal, you can have whatever you want. So it doesn't kind of force anything on diagonal. But what is important, if I put T here outside the diagonal, if I want to be antisymmetric, I must have false there. And again, if I put through here, I have to put false there. But I can put both of them to be false, that's not a problem. And then here again, so this true is related with false. This true is related with this false. And then let me do one more. So true here, then that one forces false here. Because this is position 4, 2, so on the position 2, 4, we must have false. So let me do just for trivial false. Here it is. This relation is antisymmetric because whenever I have true outside of diagonal, it is accompanied in the symmetric position with a false. That's why it's called antisymmetric. And then one more definition. If a binary relation R is a reflexive, I'm going to say on a set A, because on a set A is reflexive, antisymmetric, and transitive, then R is a partial order relation. Or just is a partial order. So like equivalence relations, but symmetric was traded for antisymmetric. And then we also say that A together with R is a partially ordered set. It is. Let's see a couple of well-known examples, actually. One of them is example. If you take a real number and the standard less than or equal, by the way, how is that defined? So how is less than or equal defined on reals? We are not studying that, but there must be a way how to explain how would you write a program that one number is less than or equal than the other. Probably one can say the following: a less than or equal to b if and only if b minus a is greater than or equal to 0. But how do you test that? For example, there exists c such that b minus a equals c squared. So here's an algebraic way to describe less than or equal or greater than or equal. So anyway, what can we say about it? That's actually the partial order. So there is really smaller and larger. So you remember that idea, this whole idea of partial order relations. And so number line, so here is -3, here is -20, -1, 0, here is 1, 2. So what? 0 is less than, so 0 is less than or equal 1, but then 1 is not less than or equal 0. And that's exactly why it is really anti-symmetric. It is transitive. It is reflexive. Every number is less than or equal itself. Then here's another example. In our notes, that's example 653. We have set A, B, C, D. But then we'll not define the relation on A itself, but we'll define relation less than or equal. That's standard way how we label relation, partial order relation. We'll define less than or equal on the set of words on A or strings on A. So how do we define that? Word W1 is less than or equal word W2 if, let's go lexicographic ordering of words, like in the phone book. So if there exists I from Z plus, such that so on that ith letter, so before that, they have the same value. So it's not just for every j less than I, W1 of j equals W2 of j. So before that index I, they have the same value, and on that jth plus, actually, yeah, we can define it that way. It might be better to define it like this: strict order. And then W1 of I is less than W2 of I. If we have order like this is not really partial order, it is strict order, because no element is smaller than itself. So for example, if I have word A, B, B, C, and I have word A, B, D, D, or whatever, then what? We check first letter, equal, keep going. Second letter, equal, keep going. And then here is that I in the definition. First time when they are not equal is on spot number 3, so I equals 3. And then since if this is W1 and this is W2, then we'll say that the W1 is less than W2 lexicographically if you make a well, like phone book, then this name will come before this one. And then you can say, yes, but this is not partial order because it's not reflexive. Then we say the following. Now we define the following relation. W1 is less or equal to W2 if and only if W1 is less than W2 or W1 equals W2. And that's always how we get, if you have so-called strict order, how do we get less than or equal order that allows and has actually a reflexivity. And then, but what's bad about both these examples, they might give you the wrong impression that partial orders are always what we say linearly ordered, totally ordered. What's special about these total orders? Whenever I pick up two elements, I can tell you who's bigger, who's smaller. So every two elements are comparable. Partial order doesn't mean that always, and actually very interesting partial orders, particularly those that we'll study in chapter 7, graphs, actually are usually not linearly ordered. So there are incomparable elements. That's why actually the best example is the one that I want right now. And that example looks like this. The example is we take numbers from 2 to 10. So A is 2, 3, 4, 5, 6, 7, 9, 10. And we'll define relation. How did I call it? R, I think so. A, R, B, if and only if A divides. And that's really, this is a partial order. It is a partial order. It's easy to check. Actually, we showed that in one of the earlier chapters, that actually it is reflexive, so every element divides into itself. If A divides into B and B divides into C, A divides into C, and that's also true. We have one of the theorems before. Why is it anti-symmetric? If A divides into B and B divides into A, and they are both positive numbers, then A must be equal to B. Because if A divides into B, it must be less than or equal than the same way here. So it is really reflexive and transitive, and here is anti-symmetric. But here's what happens here. If you take 3 and 5, 3 does not divide into 5. But neither 5 divides into 3, so that's what we say, they are incomparable. And then for those partial orders, very often it helps to draw a little diagram, who is related to what. So here it is, so we can say the following. 2 is here, 3 is unrelated, because none of them, so we put them on the same level. And then what, 5 is here. Actually what, you can see easily who's on the bottom. Numbers that nothing divides into them except the 1, and that number, that means prime. So primes are at the bottom. So 2, 3, 5, and 7. And then what happens? 4 is above 2, so here is 4. So 2 goes into 4. Then 5 is already there. Then 6 is here. And then we connect 2 divides into 6 and 3 divides into 6. Well, 7 is already there. 8 is even on the 3rd floor because 4 divides into it. 4. And then who else? 9 is there. So 3 divides into 9, the only one. And finally, where do we put 10? 10 is somewhere here, let's say. And then we say, well, we'll use different colors so that you don't mix them up. Let's say blue. So that 2 divides into 10 and 5 divides into 10. Here is the diagram that actually records who divides into what. Usually element is below on the lower level and there is connection. So for example, 7 is lower than 9, but we didn't connect them, so it doesn't mean that they are related. So you see how this doesn't look linear at all, and that's where the word partial order comes. So we use linear orders for those where every 2 elements are related, one way or the other, Those are partial ordered when some elements are not ordered. And then what? Here's one more thing we want to learn, and that is, if we have a partial order, can we enrich it? That means make more connections so that it becomes linear order. So an example. So we say the following: if we have relation R here, can I make it bigger into relation, let me call it S, so that S is linear? And the answer is yes. How are we gonna do it? We'll say the following. On the bottom, we will put the lowest elements. So we'll put 2 here. And then, who is the next one? Now we put on the bottom elements that actually nobody's below them. But now we need to compare them. We'll do it in an artificial way. So we will add a new connection between 2 and 3. So they are unrelated. This is now S enrichment. So 3, then 3 is below 5. Why didn't we do 5 below 3? We must have something, some rule in the program when we say if elements are incomparable, then we'll compare them in their traditional order, how they normally go with their value. So 2, 3, 5 is here, and then who is the next one? 7. So here are elements that generally by putting them here on the bottom, we are not into risk into making something ruining anti-symmetric. Here it is. Now we are done with them, then we'll look at the second floor, 4 and 6. And then again, doesn't matter, as 4 and 6 must be above 2 and 3 because they are related with 2 or 2 and 3. And then we are not ruining anything by putting them now above. They connect, they follow their previous connection. So we'll now go with 4 here. And here we'll put 6. We can do it the other way around. As I said, you just inherit. So those old connection between 2 and 4 is still active. So 2 and 4 is the old connection. 2 and 6 is the old connection. And they are not contradicting transitivity with those newly established connections. And then we are done with the second floor. Now, actually, what? Why did I shouldn't put 9 and 10 on the third floor because they have only factors from the primes. No? It doesn't matter, but it's very nice property. So here is 9 should be here, and then 10 should be here. They should be on the third floor. This one has 2 predecessors. So that's why that one should be on the third floor. So doesn't matter. So 7, 4, 6. Now we also put 9 from the second floor. We put 10, and now here are some connections are old, some of them are new, and at the end, someone from the third floor. Why do you do that? Because you want to make it sure that you included everybody from second floor before you do the third floor. You put 8 on top, and here it is. So what did we accomplish? We have a linear ordering that actually enriches the old one. That means if someone's connected in the old ordering, like 2 and 8, then 2 and 8 are also connected here. Generally, when we have linear order, we don't write those other connections. We just draw the connections with a neighbor, and because of transitivity, we assume that if I have connection between 2 and 3 and 3 and 5, 3 is connection between 2 and 5, I don't have to draw it. So that's a cleaner picture. With that convention, it's much nicer. So for example, I have connection between 2 and 8. Do I have it now? Yes, 2 and 8 through all these new members. So that's actually one easy algorithm, how you can always enrich partial order to become a linear order, and that's all for this section.